Somewhere on the far side of the galaxy, the James Webb Space Telescope just recorded a sight no one thought we'd ever see. In a stretch of space dominated by a supermassive black hole, Webb's sensors picked up a strange ripple, a distortion in light that looked less like ordinary gravitational lensing and more like the entrance to a cosmic tunnel. Then the impossible happened. A warm, structured object appeared, slowing as if drawn toward an unseen doorway before vanishing in a burst of mid-infrared energy. Scientists scrambled to explain it. They considered lensing and accretion, but the patterns and timing didn't fit. For the first time, the evidence pointed to something extraordinary, an object entering what could be a real-life wormhole. As the world's most powerful telescope stared into the unknown, we were left with a chilling question. Did Webb just witness the universe open a door? And if so, what passed through? It started on a quiet, routine evening, just another shift in the relentless silent watch that the James Webb Space Telescope keeps over the darkness between stars. Far from Earth, alone in the cold at the L2 point, Webb stared deep into the crowded heart of a distant galaxy. But across its sensitive detectors, something extraordinary flickered into view, a shimmering distortion, as if the fabric of light itself had been warped by a ripple. At first, it looked almost like the mirage above a hot road, a faint arc bending around the black shadow of a supermassive black hole. But this was no ordinary lensing event. The light danced, stretched, and most unusual of all, seemed to shift, as if responding to something passing through a hidden gate in space. Over several nights, Webb's powerful infrared eyes returned to the same spot, gathering data with the patience only a machine can have. Each time, the ripple appeared again, consistent, unmistakable, growing a little stronger before fading. The astronomers watched the data accumulate. It was like seeing a stone skip across a pond in slow motion, said Dr. Mai Lin, one of Webb's lead imaging specialists. Except this pond was space itself, and the ripples followed rules we've never seen before. They poured over the images, a faint shimmering arc, then gradually a structured silhouette, something with an edge, seeming to drift toward the center, pulled inexorably toward the dark core. Skeptics were quick to point out that gravitational lensing, where a black hole bends light from behind it, is common. But Webb's data was different. This was not the classic perfectly curved Einstein ring. Instead, the light was being twisted in a way that suggested structure, something passing through or into the black hole, not just around it. The pattern changed over time, like a shadow slipping through an invisible doorway. If this is lensing, Lin noted, then it's lensing with choreography, like someone's moving through a curtain, not just peeking around it. Naturally, the first priority was to rule out technical errors. Teams ran rigorous calibration checks on Webb's sensitive instruments. They filtered out cosmic rays, ruled out software glitches, and even checked for solar interference. But every test confirmed it. The anomaly was real, persistent, and tracked across several devices. It was not a brief fluke or a ghost in the data. The signal remained stable even as Webb's instruments rotated and recalibrated. As one senior scientist put it, this is the kind of thing you see once in a career, if you're lucky. It's not noise. It's a message from the universe, and it's not going away. As the data became impossible to ignore, the question naturally arose, what could cause such a ripple in reality? To answer that, we need to step back from Webb's eye and explore the wildest frontiers of physics, where the impossible becomes theoretical, and the theoretical sometimes becomes real. Wormholes. The term alone conjures images of science fiction and interstellar travel, shortcuts through the fabric of space. But these ideas aren't just fantasy. They were first proposed in 1935 by Einstein and Rosen, who imagined a tunnel, a so-called Einstein-Rosen bridge, connecting distant points in space-time. It was a beautiful concept, a passage that could link two places faster than light would allow. The math was tantalizing, but even from the start, physicists knew there were problems. As Dr. Vijay Patel put it, we could write the equations, but nature didn't give us the building blocks, at least not the kind you can order off a shelf. The main hurdle was stability. Wormholes, as Einstein and Rosen wrote, would collapse instantly without some bizarre hypothetical ingredient, exotic matter with negative energy. In all known forms, gravity pulls things together. But exotic matter would push space-time apart, propping open the wormhole's throat. The trouble is, we've never found such stuff in nature. It's like needing anti-gravity paint to build a bridge, explains Dr. Patel, except nobody's ever seen the paint or even the brush. Every simple model showed wormholes snapping shut before anything or anyone could get through. But the story doesn't end there. Physicists kept looking for loopholes. In the 1980s and 1990s, theorists proposed traversable wormholes powered by negative energy, perhaps harnessed from quantum effects or even dark energy. These models are still speculative, but they show that at least on paper, it's possible for a wormhole to stay open long enough for something to pass through. The idea sparked new hope and decades of debate. If you find a wormhole, says Dr. Lin, you've basically won the cosmic lottery, and the ticket is quantum weirdness. A newer twist came with the ER=EPR conjecture, a theory that links wormholes to quantum entanglement, suggesting that entangled particles might actually be joined by microscopic bridges in space-time. It's a radical idea hinting that the universe is woven together in ways we're only starting to understand. Yet for all the talk, there is still no direct evidence that wormholes exist. The search continues, not just with equations, but now, for the first time, perhaps with telescopes like Webb. With this new context, the images from Webb take on a new light. For the first time, we're not just theorizing. We might be seeing the real signature of a wormhole in action. But how did Webb, of all instruments, make this possible? The answer lies in its unique position, its cutting-edge technology, and a little bit of luck. Webb's superpower is its ability to see the invisible. Where older telescopes watched invisible light, Webb peers deep into the infrared, catching the faint heat glow of objects billions of light years away. This is crucial because the regions around black holes are hidden behind thick clouds of dust and gas, opaque to regular telescopes, but transparent in infrared. If something is slipping through a wormhole or diving into a black hole, it's likely to be warm, to glow in ways only Webb can see. Infrared is the language of the universe's secrets, said Dr. Alicia Ramirez, a Webb project scientist, and Webb is the world's best translator. Its vantage point at the second Lagrange point, or L2, gives Webb a perfect, undisturbed view, 1,000,000 miles from Earth, floating in a stable pocket of gravity, shielded from the sun, moon, and our noisy planet. This stability allows its delicate instruments, like NIRCam and MIRI, to take long, uninterrupted exposures, building up a picture pixel by pixel. Time series imaging lets scientists track changes frame by frame across days or weeks. Every photon counts. Webb is like a time-lapse camera for the cosmos, Ramirez explained. It lets us see things not as snapshots, but as stories unfolding. Webb's recent observation programs have leaned into the unpredictable. Instead of only staring at ancient galaxies, astronomers have started using Webb to hunt for dynamic events, brief, mysterious phenomena that can't be seen any other way. Anomalies like the one now dubbed the Ripple are exactly the kind of things these programs are meant to catch. Every filter and mode is pushed to its limits, giving scientists not just a static image, but a multi-layered data set to comb through. It's like switching from black and white to 4K color video, said Dr. Lin. Suddenly, you're seeing things you never knew were there. To be sure that what they were seeing was real, scientists ran Webb's data through a gauntlet of checks. They compared it with images taken using different filters, different detectors, and even different times of day and orientation. Every time, the anomaly stayed put. Nothing in the pipeline, no cosmic ray, no simple flare, could explain it away.